Hey math friends, this is AP Calculus section 2.8 day 2 notes. Today we're going to just briefly talk about derivative notations. Now that we have this idea of the derivative of f of x being a function itself, we've been labeling it as f prime of x. Okay, and that's for now either y prime or f prime of x. These two are kind of going to be our common notations. Later in the course, we will be looking at other ways to write the derivative. Dy dx will be a common one. That just means the derivative of y with respect to x. Now there are a lot of other notations that are listed here. df dx, d dx of f of x, d, big D of f of x, and d with that little subscript x of f of x. These are just different notations that you may see if you're looking at videos on the internet, if you're watching TikTok and somebody's talking calculus. If you look at a different textbook, perhaps you'll see different notations. But our textbook uses the f prime of x or the y prime notation, and then later when we talk about implicit differentiation, we will be using Leibniz notation, which is this dy dx. Leibniz is the guy that came up with that notation. Okay, so just be aware that there are different ways to write the derivative, but they all mean the same thing. Example 2 gives us a table of information, and it says let P of t be the percentage of Americans under the age of 18 at time t. This table gives us values of this function in census years from 1950 to 2000. So notice that every 10 years they have a new population value because they conduct a census every 10 years. And if you weren't aware of this, we are in a census year. 2020 right now is a census year. All right, so part A asks us, what is the meaning of P prime of t? Okay, well, for part A, remember that derivatives are rates of change. So if our table is giving us population and percentage of Americans under age 18 at any given time t, then P prime of t is going to be the rate of population change of Americans under age 18 at any given time t. And our units for this derivative, because we're talking about a percentage of Americans under the age of 18, our units would be percent per year for our derivative. All right, letter B says construct a table of estimated values for P prime of t. Well, since we only have a table, right, we don't have a function to work with here, the best that we can do is calculate a bunch of slopes, right? And so our P prime of t values are going to be equal to the next consecutive point, the y value of that, so P of t plus 10 minus P of t divided by, and then when we subtract the years, we're always 10 years apart, so our denominator is always going to be 10. So if we build a table of years, starting with the year 1950, and we're just going to do the math here. So we're finding slopes for P prime of t. All right, so if t is 1950, then P of t plus 10 would be P of t for 1960. So that's going to be 35.7 minus P of t, so minus population in 1950, which is 31.1 divided by 10. You grab your calculator. This gives you a slope of 0.46. In 1960, P of t plus 10 would be population in 1970, so that's going to be 34.0 minus 35.7 divided by 10, which gives me a slope of negative 0.17. In 1970, P of t plus 10 is going to be the y value of 1980, which is 28.0, minus P of 1970, which is 34.0, divided by 10, which gives me a slope of negative 0.60. In 1980, we will have 25.7 minus 28.0, divided by 10, which gives us a slope of negative 0.23. And then finally in 1990, 25.7 minus, looks like the population held steady, 25.7 divided by 10 gives us a slope of 0 because our y values made 0 in our numerator. All right, so now we have a table of values for P prime of t. Part C asks us to graph P and P prime. All right, so I'm going to create a coordinate plane here, and both of my graphs are going to live either in the first quadrant or in the fourth quadrant. And I'm going to kind of use some, I don't want to call them cheating techniques, but in a way they kind of are. Okay, so I'm going to do a break in my graph on my y-axis because all of my y values for the function in the table range between like 25 and 35. So I'm going to put a little break. Here's my y-axis. I'm going to put a little break here. And I'm just going to start counting with 25. And I'm going to graph P of t first. So I've got my years here on my x-axis, which would be 1950 up to 2000. Okay. And I'm going to go ahead and I'm going to plot my points for P of t. When t was 1950, P of t was 31.1. So about right there. 1960, I'm at 35.7. 1970, 34. 1980, 28. 1990, 25.7, and 2000, 25.7. So here is what my original function P of t looks like. All right, now I'm supposed to use those ordered pairs that I just created in part B in my table to graph my derivative. Well, all of my y values of my derivative are like decimal numbers. So down here on my negative y-axis, I am going to count by tenths. Okay, so this is negative 0.1, negative 0.2, negative 0.3, 0.4, 5, 0.6, 0.7. All right. So when I plot these, at 1950, my slope was positive 0.46. So that's going to be just above my x-axis. And If I was counting by the same scale above as below, it would be about right there. And then in 1960, I'm at negative 0.17. 1970, I'm at negative 0.6. 1980, negative 0.23. And in 1990, I am at 0. Okay, so there is our graph of P prime of t. Okay, now let's pause for a second and let's think about what we know about a function and its derivative. The derivative function was derived from the slopes of P of t. So a few important characteristic locations to look at. When the slope of my original function is 0, my derivative should be crossing the x-axis. Well, where does my original function have a slope of 0? Looks like it's happening about right here, and right here is where I'm crossing the x-axis. So that lines up and that makes sense. Right here, I have a slope of 0. Right here, my derivative is crossing the x-axis. All right. When I look at the shape of my curve and I think about the slopes being positive and negative, right here on my original function, my slope is increasing and my derivative is above 0. And then my slope starts to decrease and is decreasing all the way until it crosses the x-axis. So the remainder of my derivative curve is always below 0 because my original function is decreasing. And of course, the shape of the curves come from the rate at which it is either increasing or the rate at which it is decreasing. When my original function is decreasing at an increasing rate, so from here to about here, my slope of my derivative is negative. Then I kind of have what we would call a point of inflection right here. We'll talk about that later. And my slope is changing from decreasing at an increasing rate to decreasing at a decreasing rate. And that's when the slope of my derivative starts to go back up. So these are all characteristics of the original function and its derivative that we will continue to talk about in the next few sections of our notes. The last part of this problem, part D, asked us to, or how would it be possible to get more accurate values for P prime of t? Well, that's a pretty easy question to answer. To get more accurate values for P prime of t, we need more data points for P of t. But since they only conduct a census once every 10 years, these are the only data points that we're going to get. Here to talk about derivatives and differentiability, whether you can find a derivative at every point on a curve or not. Recall from the previous section that not all functions are differentiable everywhere. They have locations where there are places that the derivative doesn't exist. And we saw some illustrations of that in our previous section of notes where we had corners or kinks, vertical asymptotes, anywhere, and jump discontinuities, anywhere where we can't calculate a limit, we can't find a derivative. So this leads us to an important definition and theorem. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval, ab, so not square brackets, round brackets, if it is differentiable at every number on the interval. If f is differentiable at a, f is continuous at a. Please note this relationship does not go the other direction, okay? If f is differentiable at a, f is continuous at a. But if f is continuous at a, it is not necessarily differentiable at a. Case in point, look at the picture for example 2. It says, for the following graphs, state the values at which the graph is discontinuous, explain, and not differentiable, explain. Well, if we look at this first picture, right away, you can see that from, it looks like, about -5 to 0, this graph is continuous, right? However, even though it's continuous all along there, we have a location here where the graph is not differentiable. We cannot calculate a derivative at a sharp kink or corner. So we would say that it is not differentiable at the location x equals -4. And this is because we have a kink. Continuing on, I see we have an open circle and a closed circle right here. So we would also say that this graph is not differentiable at the location x equals 0. And this is because the graph is discontinuous. We have that jump discontinuity there. So these are the locations where it's not differentiable. The location where this graph is discontinuous is just at x equals 0, and that's because we have a jump there. When we look at the second example, let's do our lift the pencil test. And you can see that this graph is continuous everywhere. I never had to lift my pencil to trace that graph. So as far as where this graph is discontinuous, there are no locations where that happens. This graph is continuous everywhere. However, not differentiable, well, that's another story. There are actually 2 locations on this curve where this graph is not differentiable. One of them is right here at x equals 4 because we have a kink again. And the second one you may or may not have noticed, but when I traced over it, I kind of covered it up a little bit. There's a bit of a vertical line there in our graph, or a vertical tangent in our graph. So at x equals -1, our graph has a vertical tangent. And remember, a slope of a vertical line is undefined, so we cannot calculate the derivative wherever our graph has a vertical tangent. If we begin with some function f of x, and we can find its first derivative, f prime of x, which is also a function, then why can't we find its second derivative, f prime prime of x, or its third derivative, f prime 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 of x? And we could keep going. So in general, we can interpret a second derivative as a rate of change of a rate of change. We most commonly see this when we're talking about our original function f as being the position of something that's moving. Its first derivative, f prime, would then be the velocity of that object, and its second derivative, f prime prime, would then be the acceleration. Because if the original function is position, then the first derivative would be position as related to time, rate of change of position over time, and then its third derivative would be the rate of change of the velocity, which is the acceleration. Example 3 gives us a function f of x is 3x squared plus 2x plus 1. And it says use the definition of the derivative to find f prime of x, which is our first derivative, and f prime prime of x, which is our second derivative. And then they want us to graph the original function, the first derivative, and the second derivative on the same screen to check our answers. For part A, if we're going to find f prime of x, we're going to be using our derivative formula, which is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So f prime of x is going to be equal to the limit as h approaches 0 of 3 times x plus h, quantity squared, plus 2 times x plus h plus 1. And we're going to subtract from that our f of x, which is 3, oh, and I need to put a bracket around that, 3x squared plus 2x plus 1. And this is all going to be divided by h. So now I have some algebra to do. F prime of x will be the limit as h approaches 0. X plus h quantity squared is x squared plus 2xh plus h squared. And if I go ahead and I distribute the 3 right away, I get 3x squared plus 6xh plus 3h squared plus 2x plus 2h plus 1. And then if I distribute the negative, I get minus 3x squared minus 2x and minus 1. And this is all divided by h. Now I get to cross out any terms that cancel in my numerator. 3x squared and negative 3x squared, positive 2x and negative x, positive 1 and negative 1 all cancel out. And the terms that I have left all contain h. So the next step is to factor that h out of each of those 3 remaining terms. So I will have h times 6x plus 3h plus 2 all divided by h. I can cross out my h's, and now when I evaluate my limit as h approaches 0, I get 6x plus 3 times 0 plus 2. That middle term cancels out, so I have an equation of f prime of x is equal to 6x plus 2. If I want to find the second derivative, which would be f prime prime of x, I am just looking for the derivative of f prime of x. So I start with my same derivative equation, which is going to be the limit as h approaches 0 of, and I have to plug x plus h in for x, so 6 times x plus h plus 2 minus f of x, which is 6x plus 2, divided by h. Here comes my algebra step. The limit as h approaches 0 of distribute, and we get 6x plus 6h plus 2 minus 6x minus 2 divided by h. Now I get to cancel opposite terms in the numerator. 6x and negative 6x, positive 2 and negative 2. So I am left with the limit as h approaches 0 of 6h over h, and my h's cancel. So I am left with the limit as h approaches 0 of 6, which means the equation of my second derivative is f of x equals 6. So now I have my original function, f of x, 3x squared plus 2x plus 1. I have my first derivative, f prime of x, which is 6x plus 2, and I have my third derivative, f prime prime of x, which is the horizontal line, just y equals 6. So the last part of our problem asks us to graph all 3 of these functions on the same screen to check our answers. So we open our graphing calculators, clear out anything that you have in there, and let's start with our original function f of x, which was 3x squared plus 2x plus 1. In y2, we will put our first derivative, which was 6x plus 2. That's a linear function. It's going to make a straight line, diagonal, straight line. And in y3, our third derivative, which is y equals 6, a horizontal line. So now we go ahead and we do a zoom 6, standard window to graph these three. And we can see our three functions. Our original function f of x, that was our 3x squared plus 2x plus 1, that is a parabola, right? Our first derivative is the red line, the diagonal linear function, and then our third derivative is the horizontal line. So let's talk about what we know about functions and their derivatives in terms of a graph. If we look at our original function, where it is decreasing from left to right, right here, our derivative lives below the x-axis. Then we have the turning point on our graph where our derivative is going to be 0 because slope right here is a horizontal line. Our derivative crosses the x-axis. And then on our original function where our slope is increasing, our derivative lives above the x-axis. Okay? Then we take a look at the first derivative, which is the red line, and the second derivative, which is the black line. Notice that, first of all, the red line from left to right is always increasing. So it makes sense that our second derivative, this horizontal line, is living above the x-axis the entire time. The second thing to note is that we have a steady slope because this is a linear function. The slope here is always 6. Therefore, our derivative is a horizontal line at y equals 6. So let's go back to our notes and let's sketch a picture of our three functions for future reference. So here we have our coordinate plane. We had our original function f of x, which was a parabola. We had our first derivative, f prime of x, which was a linear function. And we had our second derivative, f prime prime of x, which was a horizontal line. Our last example today is a little bit challenging. We begin by talking about the position function again, knowing that the position function would be like our f of x. So then the first derivative would be the velocity, and the second derivative would be the acceleration. Well, we could find a third derivative of a position function, and this has a special name. It's called the jerk function, which is the rate of change of the acceleration. And it's named the jerk function because a sudden change in acceleration feels like a jerk if you're in a moving vehicle. All right, so our job here is to take this picture. We have 4 different functions, and you may want to color code these on your paper just so that it's easier for you to identify them. And it tells us that one is the position, so the original function f of x. One is its velocity, the first derivative. One is the acceleration, which is the second derivative. And then the fourth picture is the jerk function, which is the third derivative. So based on what we know about the characteristics of graphs of functions and their derivatives, we're supposed to identify each curve and explain our choice. All right, so if we're in a car and we're moving in the forward direction, it makes sense to make an assumption that our position function is probably always going to be above 0. Because if we're driving in a car, we're probably driving down the road, we're probably not putting the car in reverse and going backwards. So if we try to identify our position function, which would be like our original f of x function, we'd be looking at functions on the graph that are always positive. And if we're talking about position, we'd also be looking at where it's always increasing. So I would say, just based on my picture here, that letter D would be our position function, or our f of x. And the reason that I would say this is because the function is always increasing and the slope is always positive. So let's write that down. The function is always increasing and the slope is always positive. Okay, so now that we've established that that black line is our f of x, based on that, let's try to figure out our first derivative of that function. Now, if the function is always increasing and the slope is always positive, then that means that our first derivative should always live above the x-axis. If the function is always increasing, the derivative should always be above the x-axis. Well, of the three graphs that we have to choose from, the pink one, the blue one, and the green one, the only one that is always above the x-axis is the green one. So that alone tells me that letter C has to be our velocity function, or our f prime of x. Okay, and we could say about this that as the slope of the position graph becomes steady, the slope of the velocity graph flattens. Or in other words, our slope becomes 0, right? Because if C is the derivative of D, wherever the slope is steady in D, the slope should become horizontal in C. It should become a horizontal line. All right, so now that we've determined position and velocity, our next job is to decide which one is acceleration. We have two options left. Okay, so what we're looking for in part C is, since it looks like we have a very slight, and I'm looking at graph C, we have a very slight decrease right here. I would be looking for a graph at this point right here. Our slope is going from increasing to decreasing. So I would be looking for a graph where the graph goes from above the x-axis to below the x-axis at that approximate location. And if you look at A and B, the obvious choice is going to be B. B has an x-intercept right there at that point where we said C was changing from increasing to decreasing. So I would say graph B, which is the blue graph, is our acceleration function, which is f prime prime of x, okay? And we can say that our acceleration is increasing when the slope of the velocity is increasing, and then our acceleration starts to decrease when the slope of the velocity starts to decrease, or it starts increasing at a decreasing rate. And then when our velocity is decreasing, our acceleration is negative, as we said. Okay, so you can write any information that you want to there about part B. Now, obviously, by default, that tells us that our function A here, the last function standing, which is the pink one, letter A has to be our jerk function, which is our third derivative, f prime 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 of x. And I just want you again to compare graph A to graph B, where graph B is increasing. So again, on graph B, I am increasing from here to here. Graph A is above 0. And then where graph B starts to increase or starts to decrease, that's where graph A crosses the x-axis and then goes below 0. And graph B is decreasing for the rest of the time, therefore graph A lives below the x-axis the rest of the time. But when it's When graph B is decreasing at an increasing rate, graph A is decreasing. And when graph B begins to decrease at an increasing rate, graph A starts to increase. All these subtle nuances that we look at when we're looking at graphs of functions and their many derivatives.